Inside any living cell, thousands of free-floating proteins and small molecules are constantly slamming into one another at blinding speeds. It is a chaotic environment where enzymes must somehow locate and bind to their target substrates. To make sense of this biological chaos, we translate it into a foundational chemical pathway. An enzyme, E, reacts with a substrate, S, to reversibly form an enzyme-substrate complex, ES, which then converts into a free enzyme and a final product, P. Each step of this pathway has a specific rate. The constant K+1 governs the forward formation of the ES complex, while K-1 represents the complex breaking back apart. Finally, K2 dictates the rate at which the complex successfully yields the final product. In these handwritten derivation equations, we find the mathematical starting point for all enzyme kinetics, the steady-state assumption. As the reaction progresses, the concentration of the enzyme substrate complex briefly remains constant. The rate of complex formation perfectly equals the rate of dissociation. Locking that variable in place lets us derive a baseline equation to predict normal enzyme behavior, and eventually track the exact mathematical fingerprints left behind by different molecular poisons. Looking at this set of notes, balancing formation and dissociation rates requires algebraic substitutions to solve for V0, the initial velocity. During this initial stage, substrate outnumbers enzyme, making the low enzyme concentration the limiting factor for the reaction speed. The result of this algebraic isolation is the Michaelis-Menten equation, defining initial velocity as Vmax times the substrate concentration, divided by Km plus the substrate concentration. Let's pull that equation out and define the variables. Vmax is the maximum theoretical velocity of the reaction. This is the absolute speed cap, achieved only when every single enzyme active site is completely saturated with a substrate. Km, the Michaelis constant, acts as an inverse measure of the enzyme's baseline affinity for its target substrate. A high Km means low affinity, requiring more substrate to reach half of the maximum velocity. Establishing the speed cap with Vmax and the substrate affinity with Km gives us a complete mathematical profile of a healthy enzyme. We can now test this baseline against different types of inhibitors. A competitive inhibitor is a molecular imposter. It mimics the shape of the actual substrate and wedges directly into the active site of a free enzyme, physically blocking the correct molecule from attaching. This alters our foundational pathway. We now have to add a dead-end branch extending from the free enzyme, reacting with the inhibitor to form an inactive EI complex. Because the substrate and the inhibitor are competing for the exact same physical space, the block is reversible. Flooding the system with a massive excess of substrate molecules increases the probability that the real substrate will bind, completely flushing out the inhibitor. Mathematically, this means the true maximum velocity of the enzyme remains fully achievable. Given enough substrate, the enzyme can still hit its top speed. However, reaching that top speed now requires a much higher concentration of substrate than it did under normal conditions. The enzyme's apparent affinity has dropped, which forces our Km value to increase. Competitive inhibitors alter an enzyme's apparent affinity without capping its total potential output. Not all inhibitors compete for the active site. Some bypass it entirely, binding to a separate allosteric site on the enzyme instead. Looking at our pathway diagram, this creates a different structure. A non-competitive inhibitor can bind to the free enzyme, forming an EI complex, but it can also bind to an already formed enzyme-substrate complex, creating an inactive ESI complex. Because this binding occurs at a separate location, the inhibitor does not block the active site. The substrate can still attach to the enzyme just as easily as before. The affinity, Km, remains exactly the same. But the binding of the inhibitor physically distorts the enzyme's internal structure. Even with the substrate securely in place, the enzyme cannot catalyze the reaction. It is catalytically dead. Because the machinery itself is broken, flooding the environment with extra substrate does nothing. You cannot outcompete a structural failure. With a portion of the enzyme population effectively taken offline, the functional concentration of the working enzyme drops. This forces the apparent maximum velocity, Vmax, to decrease proportionally. A non-competitive inhibitor places a hard cap on the total functional velocity of the reaction, while leaving the baseline substrate affinity perfectly intact. To translate these mathematical shifts into a practical lab diagnostic, we use a double reciprocal graph called a Lineweaver-Burke plot. We graph 1 over V0 on the y-axis against 1 over substrate concentration on the x-axis. A healthy, uninhibited enzyme reaction plots as a straight diagonal line. The y-intercept represents 1 over V max, and the x-intercept marks -1 over Km. If we overlay the data from our competitive inhibitor, the line gets steeper, but it intersects the uninhibited baseline perfectly at the y-axis. This visually proves that Vmax is unchanged, even as the x-intercept shifts to reflect a lower apparent affinity. If we clear that away and test a non-competitive inhibitor instead, the data plots completely differently. The new line pivots off the static x-intercept, while the y-intercept shifts upward, indicating a lower Vmax. That shared intersection point on the x-axis is absolute proof that the enzyme's baseline substrate affinity remained perfectly unchanged, while its maximum velocity degraded. Looking at this textbook plot for uncompetitive inhibition, the lines do not intersect at all. Instead, we see parallel lines moving outward, emphasizing exactly how different the data looks when a poison alters both variables simultaneously. By anchoring our models in the steady-state assumption, we map molecular chaos into rigid algebraic rules. We can read a simple set of intersecting lines to diagnose exactly where and how a microscopic poison is attacking an enzyme.